So how do I know when rearrangement occurs? So rearrangement. Well, there are three overall types of rearrangement, but I like to categorize them into two categories. First category is carbocation stabilization. So carbocation stabilization. Second category is ring strain, decreasing ring strain. So for the first category, we have two types. We have hydride shift, so H shift, and methyl shift. So for the hydride shift, I'll give you an example of when a hydride shift would occur. So a hydride shift would occur in an example like this. So if you have the following carbocation is an intermediate in a reaction, what can happen is this is a secondary spot, right? And that's a tertiary spot. So if this hydrogen just moves to the secondary spot, the charge will no longer be on the secondary spot. Instead, if the hydride moves, I meant to say hydride before, if the hydride moves to the secondary spot, the carbocation will now be on the tertiary spot. So you'll wind up with this. Now this is a more stable carbocation because the carbocation is on the tertiary spot. So for the case of a methyl shift, let's say you had something like this. Almost the same exact scenario as before, except this is a methyl, not a hydrogen atom. So in this case, you can actually stabilize this molecule by, again, causing the positive charge to shift from a secondary to a tertiary spot, and this can happen by moving this methyl over. So in this case, the methyl will move over, and that will cause this carbon to be stabilized, and this carbon right here will now have a positive charge, which turns out that it turns a secondary positive charge into a tertiary positive charge, and we know positive charges on tertiary carbons are more stable than positive charges than secondary carbons, and that is because of the inductive effect and hyperconjugation. Now, these overall have to do with stabilizing a carbocation by causing the carbocation to shift to a more substituted spot. Move on to category 2, we have something called a ring expansion. So ring expansion, let's say I had something like this. Okay, so positive charge is right here. We know that the most stable ring is a 6-membered ring. And the closer you get to a 6-membered ring, so to become a 5-membered ring from a 4-membered ring, is also favorable. But 6-membered ring is the most optimal. So in this case, we have a 5-membered ring, and we have a positive charge right next to the 5-membered ring. So in this case, we're actually going to have a ring expansion where you take this carbon-carbon bond and shift it over, and the positive charge is now going to wind up on this carbon. So I'm just going to count carbons, even though it doesn't really matter in this case, but it's good to do so. So 1, 2, 3, 4, 5, 6, and so the positive charge is going to wind up on 5. So 1, 2, 3, 4, 5, 6. Positive charge is on 5. Let's just put this over here. So that's the ring expansion. If you notice, now the ring expansion can only occur, when the positive charge is on a carbon, only one carbon off of the ring. So it will not occur in this scenario. And likewise, to go back to hydride shift and methyl shift for a second, a hydride shift cannot happen, let's say, in this scenario. It's 2 removed, okay? So that positive charge is 2 removed from the hydrogen that can shift. Now this hydrogen might be able to shift, but it won't happen because it's not a favorable process because it's going from secondary to secondary. And likewise from methyl shift, you see the same concept. You have positive charge there. This methyl will not go over here. X will not. So these are carbocation rearrangements and when they can occur. So now let's move on to Markovnikov versus anti-Markovnikov. So the way I'm going to do this is I'm going to draw a typical alkene. This alkene has has 2 carbons. Each double bond, the double bond on this, has 2 carbons. In this case, this is a more substituted carbon, and that's the less substituted carbon of the double bond. So I'll draw it like that. Because if I were to undergo this molecule to undergo a reaction, and it would add molecule X to the spot where the most substituted carbon is. This is an example of Markovnikov. So I'll just write N for Markovnikov. Now, if I have the same molecule, but in this case, molecule X wound up here. This will be anti-Markovnikov. An anti-Markovnikov addition, in that the molecule X would get added to the less substituted spot from the double bond, so this carbon. Whereas in Markovnikov, it was this carbon. So an example of Markovnikov addition is oxymercuration. An example of an anti-Markovnikov addition is hydroboration. So anyway, Markovnikov molecule gets added to most substituted spot, anti-Markovnikov molecule, so anti-Markovnikov molecule gets added to less substituted spot. Anyway, I hope you enjoyed this video, and thanks.